So why do we have to understand buffers in biochemistry? Basically, we have to think about whether buffers are important to physiology, right? So our blood has a pH of 7.4. We call this physiological pH. And I wanted to think what might happen to us, for example, if we just chug a whole gallon of lemonade that has a pH of about 3 and our blood isn't buffered. Will the enzymes in our bodies continue to work if the pH drops dramatically? Will the organs in our body continue to function if the pH changes? Let's talk about how buffers work, and then we'll talk a little bit more about the fact that, of course, yes, our blood is buffered. So, as we jump into talking about buffers, let's remind ourselves what we already learned about buffers in Gen Chem. We learned that buffers are strongest when pH equals pKa, of course, plus or minus 1 pH unit. And so, to understand why this is true, we're going to look closely at an example here of dihydrogen phosphate that has a pKa of 6.82, and we are going to compare it to 3 other weak acids. And we're going to do that by looking at this graph shown to you on the right. So let's talk a little bit about what we're seeing on this graph before we jump into looking at these 3 acids. So across the x-axis, folks, we have protons dissociated per molecule. So how many molecules of these different acids have lost their proton? On the left-hand side of the axis, what you're seeing 0, that would mean the molecules have all of their protons, none have left. And on the right-hand side of the axis at 1.0, that's when every proton has been lost, and we have all conjugate base present. Up on the y-axis, folks, you see pH, so we'll be looking at different pHs, how many protons have dissociated for each of these 3 molecules. And let's just start by looking at a pH of 6.8. At a pH of 6.8, how much acid and how much conjugate base are present for each of these 3 weak acids? And I want us to start with phosphate. So we're going to go to 6.8 on the y-axis, and I drew a line across the graph to show when the pH of 6.8 crosses all 3 lines. It crosses phosphate right here in the middle of the graph. Now, if we take this and we drop it down to the x-axis, you can see that 0.5, so half of all molecules will have lost their proton, okay? So now let's write this down and start comparing what the proportions are of acid and conjugate base for each of these 3 weak acids. So for phosphate at a pH of 6.8, we just saw that we'll have 50% acid form, 50% conjugate base form. Let's take a look next at the curve above phosphate. This is ammonium. And so the pH of 6.8 crosses that curve all the way over here. If we drop this down to the x-axis, we're at, I'm just going to estimate here, maybe 1%, 0.01 ions dissociated per molecule. So that means we're mostly in the acid form for phosphate. So we'll call it 99% in the acid form, maybe 1% dissociated into the base form. Now if we finish up here, excuse me, and we take the pH of 6.8 all the way down now to our last curve. This is acetic acid, and we drop it down to the x-axis. It's kind of the reverse story. Almost all has dissociated. So we're at about 99% dissociated or conjugate base form, and only about 1% left in the acid form. Now, you could argue that it's 0% and 100%, and that's fine too. But I'm going to say about 1% hasn't dissociated. So now let's take a moment to kind of think about what has happened. We see here that we are at pH equals pKa for phosphate. And when pH equals pKa, I know you already learned this, but we just saw it from the graph, there is equal amount of acid and conjugate base present. If we are now outside of pKa, like we are for the acetic acid, or like we are for the ammonium, you see that we are very much not near 50-50 at all. We basically are fully dissociated or fully not dissociated. So what we should think to ourselves is, why is 50-50 acid and conjugate base, why does that mean the same thing as being a good buffer? Buffers are resistant to changes in pH, right? Because we have equal amounts of acid and conjugate base. Imagine you're in the lab performing a titration. If you dropped a little bit of acid into a solution of 50-50 acid conjugate base for example, phosphate, what would happen is that acid would react and be neutralized by the conjugate base form of phosphate at this pH. However, let's say you're instead titrating a little bit of base, some sodium hydroxide. It could react with the acid form of phosphate in this buffered solution to be neutralized again. So, you see, because we have kind of very good amounts of both acid form and conjugate base form, a solution that is buffered at pH equals pKa is resistant to changes in pH because it has a lot of neutralization power. A little drop of excess acid will be neutralized by conjugate base. A little drop of excess base would be neutralized by the acid form of phosphate. That would not be true for either ammonium or acetic acid because they don't have equal amounts of acid or conjugate base. So they would either be very bad at neutralizing any excess acid added, or they would be bad at neutralizing any excess base added. And so that's why buffers are strongest when pH equals pKa. We have equal amounts or near equal amounts of acid and conjugate base form. And finally, in the next video, what you're going to see is we're going to kind of walk through understanding how this protonation and deprotonated, the protons dissociating, works for a polyprotic acid. It's going to be important for us to think about polyprotic acids because all amino acids are polyprotic. Phosphate is a polyprotic acid. It's actually triprotic. So it has 3 protons that can be lost. Each of these protons has its own pKa, shown by each of these 1, 2, 3 midpoints that align directly with the middle of each buffering region. Since there are 3 protons that can be lost, there are also 3 equivalence points where we have 1 proton fully dissociated, then the next proton fully dissociated, and then the next proton fully dissociated. Now, keep in mind, folks, the phosphate that I'm showing you on the screen, right, if you look at it, it is symmetrical. So which proton is lost first, second, or third doesn't really matter. They're equal to each other. Just know that each successive proton, its pKa, gets higher and higher or it becomes more challenging over time to lose those protons. Up next, let's walk through kind of visually how each of these protons is lost as we move down the curve.